In this video we're going to look at an idea called enthalpy of vaporization or latent heat of vaporization. So the symbol for that is delta H effectively, but it's got this little VAP in the middle of it. The circle means that it's a standard value. So long as we keep the following conditions the same, the value will be identical for the same substance. So the enthalpy of vaporization for water is always the same under these standard conditions of one pressure, etc. The key things we need to keep in mind is that it's going to be 1 mole of the pure substance at its boiling point. So we're looking at this orange part of the graph here. This is a heating graph. We've got the liquid phase already, and as we heat it, the particles move further apart. As they do so, they move faster. That increase in average kinetic energy results in an increase in temperature. That's why we see it going up. Then it gets to a point, its boiling point, where there's no increase in temperature for a while. We're still putting heat energy in, so where is it going? Well, that heat energy is breaking bonds. It's breaking the bonds between those in the liquid phase, turning it into the gas phase. And that's where our enthalpy of vaporization comes in. The amount of energy required to boil or evaporate 1 mole of a substance in its liquid phase, so turn it into its gas phase, at its boiling point, so for water that'd be 100 degrees, is its enthalpy of vaporization. Now I'm hoping that you've looked at the enthalpy of fusion one beforehand, and it's exactly the same idea. The difference is that the enthalpy of vaporization is always going to be higher than the enthalpy of fusion for any substance. And the reason for that is that to melt something, so to turn it into the liquid phase, just requires some bonds to be broken, enough for it to flow or become a fluid. So you're just breaking some bonds. That doesn't require nearly as much energy as vaporization, where you're breaking every intermolecular, or if it's an ionic bond, every bond between every particle so that they can escape. So remember, it's trying to get all of that turned into a gas. You're not going to see an increase in temperature until all of the substance has been evaporated. Then we're assuming that you've got a closed system, so a container, so that you can further heat the gas. But what we're looking at for this enthalpy of vaporization is this orange part of the graph. We're putting heat energy in. Where is it going? It's going into breaking bonds. And it is higher for vaporization than fusion because this is completely breaking all of the bonds so the particles can escape the substance, which is sort of our definition of a gas.